Okay, so Pebbles, how do they you get your earphones in?
Yeah, I'm going back to the last class.
Why don't you watch that? So how does Linux support the idea of universal I/O? Largely?
No wrong answers.
Actually, that was yesterday.
You said you watched all the videos.
With a POSIX compatible system on it, if it's written to the if it's a POSIX compatible version of the Linux on it, if you stick to that standard, it'll be essentially give it a universal form of I/O.
Okay, but how does it give it a universal I/O? How does Linux accomplish that? So you just babbled about POSIX?
Yeah.
Yeah, that's not right. Go ahead.
Every file has their object has the read, write, open, that stuff.
Mhm.
So no matter what you're doing, you're always able to do that, and then that object knows how to respond. With that.
Okay.
Basically.
So that's a kind of a roundabout way of saying, I mean, at the end of the day, what does Linux do? Linux treats everything as a file. Everything as a file.
Everything's got a standard.
Whether it's a device, whether it's a directory, whether it's a file, it doesn't matter. Linux treats it as a file. Okay? So it supports I/O because files have a standardized, open, close, read, write API associated with them. And if everybody's treated as an abstraction of one of those guys, then you have universal I/O. Okay. Good work, Pebbles. All right. So let's see. We were talking last time about the environment list. How every process kind of has its own global variables, if you will, and that's shared between child processes after a fork system call. Gabe. Let's see. Let's keep going here. So we were talking about memory mapping right at the end last time. So mmap creates a new memory mapping in the process's virtual address space. So this is related to this environment variable list thing. So every process kind of has its own little local environment. All right. So we talked last time about the built-in memory in that environment, this environment list, where we can kind of add variables to that guy that are available to an individual process or children of that process as the result of the fork command. Well, similarly, a process can generate brand new memory. They can say, okay, well, I'm not going to use the built-in environment list you gave me. Instead, I need to create a chunk of memory for something. And similarly, that would also be shared among children as well. So this is kind of an inter-process communication type of tool. So this can happen through two different things. File mapping, so this maps a region of a file into a calling process's virtual memory. So we could kind of protect an individual part of a file. This would be kind of related to file locking. If you've heard of things like that, we'll talk about some of those things, but it would be related to that. And then this idea of anonymous mapping is kind of a process just saying, I need new memory, I'm going to do with it what I want, as opposed to grabbing an existing element and bringing it into a shared memory spot. So maybe the difference is whether or not you pre-fill it with data or you start with a blank slate. So this one says it's initialized to 0, so you can start doing whatever you want. So memory mappings support inter-process communication between parent and child processes. Let's see, private versus shared. Shared is inherited by children, private is not through the fork system call. So you can specify that new memory you can specify that the result of memory map is only available to this parent so that you don't expose it. This would be a security issue to child processes. Maybe specifically in a situation where a parent spawns many child processes. Let's see, other uses. Storing text associated with a process, zero-filled memory associated with the process, file I/O, inter-process communication. So this kind of goes back to this idea when we talked in the past about maybe sharing a card, you keep the keys in a single drawer. So think of creating an anonymous shared memory as like a singleton. Okay, static versus shared libraries. So we have this idea of libraries on the system, and the Linux comes with a whole bunch of pre-built libraries. You can also write your own libraries that you want to make available. So the idea of a library would usually be kind of a collection of function calls that do something. Usually it's going to be related to, you'll have one file that's a library for doing, socket type function calls like sockets.h, things like that. And now you have to decide, how do I bring these libraries into my project? Okay, so there's a couple different ways. You can either statically link them, or you can link them as a shared library. So the idea here is, if you statically link a library, you get the current version of that library as part of your executable. So if you're writing a program and you're building it and you're going to release it, while that's compiling and ultimately linking is the process of bringing external libraries in. If they're statically linked, you get a copy of the current state of that library included in your executable, making your executable larger. But if it works today, it will work tomorrow, it will work the next day, until you get to the point where that library that you statically included is no longer compatible with the operating system. Because any changes to that library, like if that library changed tomorrow and you had statically linked it, your application is not benefiting from that new change. A statically linked library is included in the executable, as opposed to shared libraries where your executable references, kind of like a pointer, a library that exists in the operating system. And every time your application runs, it's referencing the current version of that library with bug fixes, bug additions, things like that. So what are the pros and cons of a statically linked library? When would you choose to statically link a library into your executable?
If you know that it's never going to change.
Okay. Well, if you know it's never going to change, then why wouldn't you actually shared?
Well, I mean,
why not keep your executable smaller? Okay.
But if you know that it's not going to change, then you can use static.
Okay. Give me a.
Would static be considered faster?
Mm,
So if you needed something like immediate access.
Arguably, you could say that. Yeah. I don't think it'd be great because you're accessing things locally, and the library is available to you either way. And the only difference would be whether you're looking in the current directory or you're having to map it outside of that. So marginally faster, but I don't think that's a real great argument. Go ahead.
If it's only being used by one thing.
It's only being used by one thing.
Like if the library is only being used by a certain process and it's not being used by a bunch of different processes, then then you could use static, because if you use static when it's a bunch of different libraries that are going to be using it, then isn't it copied multiple times?
Well, that's true. Yeah, I mean, if you have 10 programs and each of them use a library, and you statically link that library in each of them, you copied that library 10 times. That's true. But that's not necessarily a bad thing. So I'm looking for the argument when you would choose to use you would actually say, I'm going to statically link this because it's the right thing to do in this case. Go ahead. Okay, that's a reasonable answer. So kind of the polar opposite of his bad answer. So the idea would be, if you are confident that there will be changes to a library, and you feel that your application currently works correctly, and any changes made to the library will not greatly benefit you regardless, why not guarantee that your application works the day it worked the way you wrote when you wrote it, then kind of roll the dice in how your application might change through future updates of a library. Okay, fair enough. I think that's a good reason. Any other good reasons? Go ahead.
If you're developing for an older library set, if you're trying to update legacy code or something,
Okay, why?
because the current library may not function the same way as the old one once did.
Oh, okay. So you're saying if you have access to multiple lineages of a library,
Right.
and you specifically are including an older version of it because it does something that you needed to do, or maybe it has a vulnerability that you're able to take advantage of.
Sure.
Well, now at that point in time, it's essentially, I need that exact version. Updates are completely out of the question. So it's the extension of what he said. What he said is, if I know it works this way now and I don't want to risk it not working in the future, let's make it static. You're saying if I know it works now and I know it won't work with any changes in the future, because it's very reliant on some issue or something with the library you're currently using, then you might statically link it. Okay, good. One more positive that nobody's hit on yet, but both of those are very reasonable. When you write an application, especially given this, we've been spending some time talking about this idea of Posix. So we have multiple Linux operating systems that exist today, and Unix operating systems that are all Posix compatible and all written for the same architecture. So the Intel architecture, right? So given that, as long as if your library adheres to the standard, is there say that?
It's portable.
Man, you're not as big of an idiot as you look. Wow. Why didn't you come up with that, Pebbles?
I was.
You don't even know what he said still, right?
I mean,
Said it's portable. So what if you're not necessarily sure that a library that your application relies on will necessarily be on a different system? But if it's a POSIX compliant library, you know it'll work on that other system. So now you can make your application, while larger, you'll make it portable within reason, in that same as long as you're on that same architecture and that kind of stuff, and you start playing with fire a little bit, even jumping between 32-bit and 64-bit architectures. But generally speaking, if you're moving from an Intel platform to another Intel platform, even if it's a different distribution of Linux, if they're both POSIX compatible, which by definition Linux is, your application is now portable because you statically linked your libraries. Might be 4 times the size it would be otherwise, but you're not reliant on libraries being present on that destination distribution. Make sense? Okay, so I think those are some pretty good things. Then the alternative side is when should you use a shared library?
When you want your program or whatever you're making be more compact, and you know for sure that those libraries are going to be there.
Or at the very least, I guess we never know anything for sure.
Or the
but
odds are
that
in your
trade-off,
favor.
I mean, if you're doing something fairly trivial, that let's say we're writing something out to we're printing something to the screen. Okay, something that we've been doing in Unix since day one. Okay, probably not something that they're changing drastically in terms of the mechanisms for doing it. With that in mind, it probably would not benefit you to statically link the standard I/O library. There's a very, very high chance that's going to be in every distribution of Linux, and it will be compatible with what you're trying to do. And frankly, if you get to a distribution of Linux that does not support standard I/O, that it doesn't seem possible to be. So many things are completely reliant on that. I mean, that's like the most basic library that you're like guaranteed to have there. So if you're trying to minimize the footprint of your application and it only uses very standard libraries that you all but guarantee will be on every machine, and you're using them in a very standard, generic way, why statically link it if you pretty much know it'll run on any machine? Might as well reduce the file size. And then also, you have the built-in benefit of any security fixes, right? If you statically link something that has a horrible security flaw in it, and you made the wrong choice, like you didn't have to statically link it, you just either accidentally did it, or you didn't know the difference, or just that was the command you copied off of the Google, right? Then you might have an application that is vulnerable to some security flaw because of one of its statically linked libraries, where maybe that library's been patched multiple times since that problem was found. All right, so we kind of understand the pros and cons of both. One's not necessarily better or worse than the other one, but they do makes a difference. This is kind of related to the idea of, like, just in programming, pass by reference versus pass by value. One's not better or worse than the other, but we have to understand the implications either way. Okay, and some of this stuff we've talked about before in the operating systems class. I'll zip through this a little bit. So inter-process communication and synchronization stuff. So inter-process communication is how multiple processes talk to each other, whether it's parent-child processes or just processes on the system. What does synchronization mean? What's the difference between inter-process communication and then the concept of synchronization? Go ahead.
That's kind of like the singleton versus the mailbox kind of thing, where the inter-process communication is you are waiting for like you're just sending the message and then not worrying about it until, depending on what the process is. Where synchronization is two processes are it has to wait to continue until the other one's in line with it.
Okay. I mean, I think some of what you just said is true. Yeah, so maybe the easiest way to look at it is inter-process communication is generically discussing how processes can talk to each other. Okay, doesn't really talk about resource protection. Where synchronization really talks about protecting access to a resource. Whether we're limiting only one person can access a resource at a time, or we're controlling the number of elements, the number of processes that can access a resource, we are synchronizing a resource to protect processes from kind of screwing up each other's work, that type of thing. Where inter-process communication in general is a very general term. How do I send stuff between two processes? Generally speaking, synchronization is very limited on what you can do with it, but it has to be very good at what it does. And so synchronization is what we talk about, and that's where we have that conversation about atomic actions. What does it mean for an action to be atomic? At the very least, it acts like it occurs in one CPU cycle. Whether it truly uses one CPU cycle or not is relatively insignificant, as long as it locks down the CPU or changes the mode or something, so that from the rest of the operating system's perspective, it's as if it happened in one cycle. That way, two things cannot do, it can't be, it's non-interruptible. It's non-interruptible. What's up? Uninterruptible. Non-interruptible, uninterruptible. Yeah, I don't think non-interruptible is wrong, is it? I don't know.
I think it's
Might be.
It's not how people usually say it, but I don't think it's wrong.
It could be. I don't know.
Probably uninterruptible is more better.
More best?
Interruptible is a thing, I think.
Well, whatever. Punchline is that synchronization becomes, they're very simple things that must be atomic because of the job they're trying to solve. Where inter-process communication, or let's call them more powerful tools, are solving a different kind of problem, but they're facilitating various ways for two processes to exchange data. Sometimes this is simpler ones like signals, okay, where if all of you in here wanted to be aware of an event that might occur related to me, okay, so, but you're not really waiting for information from me. You just want to be aware when that event occurs, right? So when I say, okay, I'll see you on Wednesday, that's kind of class is over, so you're all going to start packing up and stuff like that. Well, you didn't really care what words came out of my mouth. You weren't like processing them. All you cared is the signal about class being over, right? So that's what signals are. It's able to just kind of flag an event has occurred. Very simple, but we don't need anything more complex than that. As opposed to if I'm sending some secret message to Tim, now I need to have a mechanism for passing data from me to him. I might need to have that data be secured. That data He might be on the same machine as I'm on, or he might be on a different machine. That's going to dictate what kind of interprocess communication I use. So things like that. Okay, so signals, this would be interprocess communication notifying events. Pipes, so this would be communication, let's call this full duplex communication between two processes on the same machine. Sockets, full duplex communication between two processes on the potentially on different machines. They don't have to be. What does it mean when I say full duplex?
Communication goes both ways at the same speed.
Well, same speed is fair. I would say that's commonly. I don't know if full duplex specifically defines that, but certainly synchronous typically defines that. But regardless, definitely that it's a two-way street. That's what full duplex says. So if Tim and I are talking in a full duplex mode, he can send stuff to me, I can send stuff to him over the exact same channel. As opposed to half duplex where only one of us can send something at a time, and then also we have input-output streams where maybe I open an output stream to you where you're a listener, and all I can do is send stuff. If you want to send stuff back to me, you're going to have to open an output stream to me, and I'll have to accept that as an input stream. So now we're communicating over two separate channels. So different technologies support these things in various ways. Let's see, file locking. This is kind of related to the memory sharing thing before, where we might lock regions of a file to prevent changes. So let's say we're if one process is making a change to a file, we might want to lock that region of the file so nobody else can make a change to that file. And as soon as we're done, we'll unlock it. Well, that would be a situation where it needs to be, that locking mechanism needs to be atomic. That way somebody doesn't sneak in and write something in that file in the middle of me locking the file down. Okay? Message queues, exchange packets data between processes. This kind of works like a mailbox. So you kind of have a place where we just throw the message and other people can come in and check the message. Semaphores, this would be a synchronization tool. You know, this is an atomic operation, acts like an integer, where you can control how many processes can access a resource at once. Or you can think of it the other way. How many copies of a resource do we have? Think of it as like a bouncer at the door. Okay, if you have put a bouncer on the bathroom, if you have 3 toilets, well, you can let 3 people in there at once. Okay, second.
There's a sink.
I guess there is that. It's kind of interesting how we were actually able to work that example. All right. How come they don't put bouncers on toilets? And how come clubs, clubs that have have cover charges and stuff? I assume this is the case. I don't frequent these places, but I assume they don't charge to go to the bathroom, right? Well, who cares? If you're in this club that you pay to get into, and you have to go to the bathroom, you pay to go to the bathroom.
I think there is a.
Is there a law?
I know Chicago
It's
is
called
laws against it.
It's called just public dignity. I don't know. Again, that's like ethical type stuff. But
Who would want to go to a club where you have to pay to use the bathroom?
Yeah, if I see that
And
on
there's
Yelp,
puke on the
I'm
floor.
not going.
maybe there's a good bar special or
If
something.
Roller Coaster Tycoon told me anything, is that you cannot charge for the bathrooms.
Is that a thing?
It's canon.
It's canon. Like, is that an option in that?
I'm pretty sure in one of the earlier ones you can, charge for the bathroom.
But this-
Trap people in there. There's a lot of stuff you can do in.
But this works in Europe. There's plenty of places in Europe.
Yeah, but those aren't like a lot of it's not like inside places we don't pay to get into.
No, it's just like a-
Yeah.
you
a pod on the
public
street.
restroom, you gotta pay like 50 cents to get in or something.
Well, even.
Well, I think
some
that-
places in Europe, they won't let you use their bathroom.
Yeah. But I think there's places in Europe where it's like, okay, well, there's public restrooms over there. Good luck.
And there's almost never toilet paper there.
Right. Or you could pay us for this one. It's clean between people, and
Yeah,
you'll have a good experience here.
See, if anything, the worst ones are the ones that don't make you pay to get in.
Okay.
They have like the cleaning person just sitting there and staring at you. Like, we're just gonna sit here and make you guilty for not paying.
in Berlin, there's.
Oh, you mean like the fancy places that have like the guy that hands you
I've
the?
seen public restrooms that are like this.
Oh,
Are you sure it works?
so you're not talking about like the guy. Because I'm thinking like the guy that like hands you a mint and stuff and gives you, that he wants to be tipped for helping you wash your hands afterwards. That guy.
Or cover your hand in toilet
I had an interesting encounter.
I can't believe you didn't hit that guy.
Huh?
I can't believe you didn't.
It was the last thing on my mind. I had priorities.
Should have been guilt money here.
Should call him. Should have called there the next day and gotten his name and see if I could PayPal him. Do you take Venmo? Do you take Venmo? Guys, it's some sort of therapy. Okay, so shared memory, similar to messaging queues, except messaging queues are provided specifically by the operating system for a centralized place to write messages, where shared memory is a mechanism prepared by the operating system, but doesn't specifically kind of provide the server functionality for accessing and for writing messages and receiving those messages. It just creates the functionality for creating shared memory and reading from shared memory. But these two guys are going to need to be aware of those pointers to the shared memory and that kind of stuff. So maybe think of shared memory as message queues light or something like that. Okay. Threads, so this kind of is related to our idea of processes. Most of us should already be exposed to these from the operating systems class. So a single process can have multiple threads. This would be an alternative to spawning off child processes. Threads can also do a form of inter-process communication through whether it's conditional variables or they could also potentially use shared memory, although you wouldn't necessarily need that because they are operating within the same memory space of the parent process that spawned them. So using the operating system's inter-process communication is kind of overkill, since these guys have access to the entire local environment. They're all living in that same environment. Well, we have this idea of something called mutual exclusion. When I say something is mutually exclusive to something else, what does that mean?
You can't have both.
Hmm?
You can't have both.
Can't have
You have
both.
to have either one or the other.
Okay.
Like you can't have a girlfriend and a chick on the side. Relationships are mutually exclusive.
You would be living evidence that that's not the way that life works.
Wait, it should work. Back to the ethical thing.
Okay. I think what you said is fair enough. In the context of an operating system, when one process is mutually exclusive to another process, they are they're not reliant on each other. So these guys can happen independently. They are exclusive from each other. They might be working on a similar task, but what this guy is doing doesn't have any impact on what this guy is doing. So these are considered mutually exclusive threads, as opposed to threads that have a reliance. And this is where asynchronous type communication comes in, where we might have two things that are happening at the same time, but we need to control what order they're happening in. Threads have this issue because they're being scheduled by the parent process that spawned them, and they all live underneath that single parent process, and they're getting CPU time that was only handed to that parent process. Now, with that in mind, we have less control over the order in which stuff happens. So we either have to put additional safeguards in place so that threads that shouldn't finish their thing next can't finish their thing next, or maybe we make the decision of turning these things into full-blown processes where we have a little bit more control over who has access to what. At the operating system level, things like semaphores are implemented to allow to block a process as opposed to blocking individual threads. Okay, and that doesn't mean that some operating systems don't have kind of the thread version of a semaphore, but these, our standard synchronization techniques don't really have threads in mind when they're implemented. Okay, let's see. So this is more just from a user's perspective, organizational tools. So for instance, if I open up the shell here and I hit Command T, and now I have 2 tabs. I have 2 separate shells going on here. So if I launch an application in one of these shells, and then I launch an application in a different one of these shells, even though they're both shells, they're 2 separate, these are actually 2 separate terminal processes running on the machine, and one of them is the parent shell of one of the programs, the other one is the parent shell of the other program, and these guys don't really have anything to do with each other. So that's kind of where shell job control comes in. Similarly, I can operate out of a single shell, so the fact that I'm using a GUI terminal application here allows me to have multiple physical shells. Okay, but if I was out at I was telnetting into a machine or SSH into a machine, I wouldn't be able to create multiple shells through a single connection. I could connect multiple times through different windows if I wanted to. But I can also then launch applications and put them in the background and then bring them to the foreground when I wanted to use them. So multitasking does exist. It's just not the friendly version that we have. So we do have some organizational tools that allow us to do different things. So an application belongs to the shell that launched it. We have the idea of a session where anything that's happened during the current session kind of falls underneath its own kind of logging category. Controlling terminals are the guys that controlled this is kind of what I just said a few minutes ago, who controls the specific process versus if you have a single terminal and you have some jobs that are running in the background, some jobs that are running in the foreground. Well, with one terminal, you'd only have one job running in the foreground at any point in time, but you could make jobs launch in the background and then bring them back to the foreground when you need them. Let's see, pseudo terminals. Can't come up with a great example of when this would be helpful. I guess maybe for like a server when you have multiple windows for like log files, you might have a single process and you might map it to 2 different terminals. Maybe one terminal outputs standard error and another terminal is constantly catting out probably actually tailing out the log file or something like that, so you can kind of see when there were incoming connections or something like that. So 2 separate terminals attached to a single process. More just a thing, just the idea that in the early days of Unix, before we were reliant on these graphical user interfaces for providing our end user experience, we had, human beings wanted to be able to use this operating system in a more powerful way. So there are mechanisms in place that allow us to, if all we're staring at all day long is something that looks like this, it allows us to do a lot more than we might expect with a single terminal window. So there's tools in place to let us do that. Kind of unrelated to anything real, just more of a convenience thing. Okay. So now, and this becomes kind of an interesting thing, especially when we talk about inter-process communication and how long a process takes to run. So when we talk about date and time, we have kind of 2 ways of looking at this. We can look at it through the lens of real time, like actual, what time is it right now? It's 3:47 p.m. That would be real time. A lot of times on a Unix or a Posix-based system, the standard is number of seconds since January 1st, 1970. So this is roughly when Unix was born. It's kind of why they picked that date. So that gives you kind of that's usually a long, and you have a giant number that tells you the number of seconds since that happened. And this is UTC, Universal Coordinated Time. I've never actually heard it referred to as the epoch, but that's what the book calls it. But yeah.
Is it UTC when you have Universal Coordinated Time? Wouldn't it be Universal Time Coordinated?
It's not though.
Oh, that really bugs me actually.
Yeah.
Like, come on.
Yeah, I think this is written right.
It's gonna bug me.
Let's see. So that's one way of looking at time on a Unix system. The other thing, and actually I'm going to show you an example of this. All right, so the last time I restarted this computer was, I think it was a software update a week ago, so 7 days. And over that period of time, here's like the average load on the system, and it's kind of troubling.
No, you don't. You haven't spelled it third. How do you have it on the PowerPoint again? The UCT thing?
UTC.
When you Google it, it's Coordinated Universal Time. So it's actually CUT.
But
But it's still listed as UTC. That's messed up.
I think anyway.
None of those work.
So the question is, why are there 4 users on my machine?
Why are there 3 on mine? Is what I'm wondering.
Root user, do
What was that?
two more.
Well, whatever. In any case, this shows me this is real time.
Installs don't create
Can't you list the users?
accounts on Windows, do they?
No. And then, so the alternative way of looking at this would be process time. This is the time that a CPU actually, or a process actually spent on the CPU. So this is taking into consideration the fact that we have context switching, and a CPU doesn't just, or a process doesn't just run on the CPU 100% of the time. So we can ask a process, how long have you actually had CPU time, to get an amount of time that something took to run. And it adds the kernel mode time versus the user mode time. We'll talk more about that here in a little bit. And then we can actually use the time command to call this. Let's see if we can. Let's see, cat. I think we do time. And then I got to do. Let's see what's in this directory. Cat test.java. Okay, I don't think I can just time that. No, apparently I can. Okay. I thought there's some things where you have to quote commands so that they're not treated as input to this guy. Instead, they actually execute, but time must not work that way. So I timed how long it takes to cat test.java. So real time was 5/100ths of a second, 5/1000ths of a second. User time was 1/1000th of a second. System time was 2/1000ths of a second. So where's the extra 2/1000ths of a second come in? Context switching, because this was I/O, right? And that requires an interrupt. So the user time was to read in the file. Then we did a context switch, which it looks like that took 2 seconds, or 2/100ths of a second. And then this is the output of, we had to go into kernel mode in order to reach system standard output, the stream. And we talked about that last time. Okay.
Thank you, Jake.
So this is going to be something that we're going to have to be concerned about for almost every application we write. Typically, when we think about client-server architecture, the generalistic way, the first thing that comes to mind usually is the internet. Okay, well, we have a client, we have a server, we're requesting stuff. So I'd kind of like to talk about at the beginning like McDonald's. Client walks into McDonald's, the server's the person behind the register or whatever is happening behind the register. You ask for a Big Mac, they serve you a Big Mac. That's the client-server architecture. So we take that down to a generic level from a systems programming perspective. It's very, very common in an operating system for one process to ask another process for some data or some value or for it to do something, whatever that is. So we have these models set up even within an operating system that has very little to do even with end user interaction. So this client-server architecture exists all over the place. So the important thing for us to consider here is that the nature of a client and the nature of a server can mean many, many different things. Okay, in the web world, the client's our web browser. In the web world, the server is our web server. But in the real world, a client's the dude at McDonald's who wants food. The server is the person at McDonald's who's going to give you food or a food-like substance. But a client could be a single thread of execution in an operating system, and the server could be the parent process of that thread. That's a legitimate thing. So the nature of client server, those words don't tell us anything about the nature of those things. Okay, it just tells us about the architecture of the application. That one guy's requesting information, the other one is serving information, one way or another. Okay, so this is our go-to move for pretty much everything when we talk about systems programming, because we're always talking to somebody. If nothing else, we're talking to the kernel, right? That's what the definition of a system call is: things that the kernel is capable of doing, things on the kernel's menu. Okay, when you go into McDonald's, you look up at the menu. Like, does anybody actually read the menu at McDonald's anymore? We were talking at lunch today that if somebody had like a local like a McDonald's franchise, it would be really funny to put like something on their menu that's like completely out of left field, but like looks completely legitimate. Like, you know, try our new iced gravy. And just, I mean, you could always be out of it and just see, you know, almost do like an experiment how often people order that. So yeah, I'll take a medium iced gravy. Oh, sorry, we just ran out. It's been really popular. Then all of a sudden, you're like, people are asking for it like a lot. So maybe we should put iced gravy on it. This is what's wrong with America.
Deep fried ice cream.
Decent.
Yeah, that's weird. That's how you get it.
Extra butter. of iced gravy, extra butter.
I feel like that would actually.
Why do you just assume there's butter? Extra.
And no ketchup.
Yeah, why don't they have that? That would be awesome.
Right?
Like, you know how they kept the ketchup pumpers? What if they had butter delivered that way? I personally like how lazy you can be, like at Culver's. They have it at other places too, but their ketchuper is air pressure based. So you just pull the thing up and the ketchup just keeps coming out. You don't have to manually push more than once.
What Culver's are you going to? Every Culver's I go to is pump.
Oh, one in Grafton. It's not like that. Yeah. Wouldn't that be awesome if they had butter in the same thing?
I think that's what happens right before the beginning of Wally. And then
That should invent it. Sell it to salad.
Because that's the real problem with making grilled cheeses at home.
no,
Is
they do have that at the movie theaters. At Marcus now, they changed it to all self-serve butter, and now it's just a pump full of.
but you have to physically pump it multiple
no, you
times.
Just like press it in, it just like comes out.
Oh, that's awesome. Because that's the problem with making grilled cheeses at home. Is that you're like too lazy to butter the bread.
Butter on tap.
Butter on top.
Like, it would be cool if they had a bread-shaped butterer. So you just
These are all Shark Tank ideas.
so like you just lay the butter on top of this like thing and you just push the button and just
Can you make that sound effect again?
it just butters it. You start making your grilled cheese. And then you could have like industrial ones that where you could butter like, you know, like a loaf of bread at once.
Just
have it like
loaf
on
of bread in.
conveyor belts.
Why not just have the bread come?
Well, no, I don't have room for a conveyor belt.
But then
Yeah, what are you even thinking? Why? We're talking about serious stuff here.
Why not just have the bread come pre-buttered?
Huh?
Why not just have the bread come
Yeah,
pre-buttered?
why doesn't bread come pre-buttered? But in the loaf form.
Yeah.
Just bake the butter in.
Some
Yeah, but the
people
problem
don't.
is, yeah, but that doesn't give you the right taste.
Well, you don't want butter on necessarily every piece of bread.
So
You
get
That's
two
right.
loaves
You're
of
gonna make a
bread.
peanut butter and jelly sandwich. You want a buttered.
Why not?
Yeah, but have you ever buttered it? I accidentally did that once. It was delicious.
No, I guess.
I actually can't even tell you a situation where I've had butter on something and said this makes it worse.
It's like bacon.
Huh?
It's like having bacon on top.
That's it. Yeah. I mean, at some point, somebody accidentally dumped bacon on ice cream, and now it's like a thing, right? It's like, well, what am I going to do? Well, I guess you got to eat that, you know.
What do you mean accidentally?
Well, somebody probably accidentally spilled bacon on something, and then they just ate it because they didn't want to waste the bacon.
I think it's pretty intentional.
I can just see that episode of Shark Tank. You see, I like butter. I just don't like putting it on.
I don't like the time I spend putting butter on stuff. You're just sitting there breathing heavy like. You're wearing a real-time blood pressure thing. For like 15 seconds and the alarm goes off. Speaking of which, we might as well waste our last minute on this. So I was watching. We talked about a lot today. So I was watching the world. What's it called? The Ninja Warrior show last night.
Ninja Warrior.
Yeah, they had the world championship thing again, where it's like America versus Europe versus Japan. Japan sucks now. They didn't get any points. Yeah, they're terrible at it. United States is like way better, and Europe is as well. But there was this guy who was crying. He was like the guy who got second in American Ninja Warrior this last year. He like finished the thing, but got second. He was on the team, but he like 103 feet. This guy was like passing in and out of consciousness, but he wanted to compete. They had him hooked up to all these machines and stuff like that, and he didn't look good. So finally, they told him he couldn't compete, so he started crying. It was funny. Yeah, but we need to do this butter thing. So if any of you are looking for, if you're still stuck on a project for Senior 7, okay, I would have a hard time not approving that.
Just make it Wi-Fi app controlled. You can make it app controlled. So you can set the amount of butter it disperses.
That's it. Make it 3D. Mod a 3D printer to do butter.
Or how about 3D printed butter?
You need a 3D
don't
print
think
You mean like in
They
the sheet
use-
so you can make
they
like
Yeah. You use the butter as the filament.
Oh, yeah.
You have to do like you have to cool it
That's
with
what, like,
nitrogen or
fancy
something. Yeah.
I 3D printed this car out of butter. All right, I'll see everybody on Wednesday.
So yeah, so you do that.